Good afternoon, ladies and gentlemen. Welcome to Physics 20. Work, energy, power. Last lesson was lesson 3?
Yeah.
All right, so this will be lesson 4. Now, I've renumbered it. Elastic forces and energy. I put this in because I have a rubber band Gatling gun, which doesn't work at the moment, but technical details. Okay. Okay, now we talked about this last class. Some materials are elastic. That is, they can stretch. How do I word that? Stretched by a force. And when the force is removed, how did I word that? And when the force is removed, yeah. And object returns to its now, most things are elastic. So some materials are elastic. That is, they stretch by force, and when the force is removed, the object returns to its original length. So elastics are a good example. Springs are a good example of elastic materials. Human bones are less elastic, but they are stretchy a little bit. Metal bars are stretchy a little bit. Now, this leads to my favorite lesson ever, the Gatling gun. Now, normally I'd have this thing set up on a tripod, working, but gentleman that built it, the concept of measure twice and cut once is kind of foreign to him. Anyway, that's why I'm going to point fingers at anybody that gives me a Gatling gun, because he may figure out how to build one that works. So, I apply force on the rubber band, and I stretch it out. Oh, can't quite see that in the video. Come on, down, boy, down, tilt down, tilt down. Come on. Boys, puppies. Yeah, but I beat it with a stick. I'm the one that gets in trouble. Anyway, so here's Mr. Gatling gun. I am Arnold from, what was that, Predator? All right, no. So here I am with Mr. Gatling gun. Notice it's not really loaded. It's only got 2 rubber bands in it. So I apply force. Would you relax? I'm not pointed at you, because you did your homework. Oh, by the way, while I'm here, anybody not get their homework done? Nothing. Okay, now, I apply force, and they stretch. What happens when I stop applying that force? Well, what do you think happens? This. They go back to their original length. And they go flying over there, which is a lot of fun. I've got to fix that bloody Gatling gun. Fix it properly this time. Anyway, now, yes, after we do the lab, I'll let you guys play with the Gatling gun, if you do the lab properly and get the work done. Anyway, what's important to note here, I applied a force over a distance. Force newtons, distance in meters. Notice the slope, m, which is rise over 1, which is k, the spring constant. So you can measure the spring constant for anything if you know the force and the distance it stretches. Now, fairly straightforward. Oh, and this is summarized in Hooke's law after Robert Hooke, the Scottish physicist. Sorry? You're going to say something sarcastic, laddie. Say it loud so I have a chance to make a comment back. Or at least turn off the camera before I load the Gatling gun again. All right. Now, note this is negative because the elastic or whatever resists the force. Or SI. So the negative tells you a direction. It's resisting. Doesn't want to work. And like some high school students I know, but no comment. Am I naming names? Am I pointing fingers? You are. Thank you. I'm not. Okay. So a couple example questions, then I'll set you free on the lab. So far, so good? All right. So how much force do you need to stretch a a 1 centimeter by 1 centimeter by 1 meter lead bar? Be much more of a thumb. No, I think they're up there. Sounds like they're up there checking the roof. Anyway.
Yes.
So we could have been a skydiver.
True.
I would love some follow through. It's not safe.
Okay. So, come on, guys. Let's get through this so we can go do the lab and play with the Gatling gun. What's the force needed to stretch a 1 centimeter by 1 centimeter by 1 meter lead bar 2 millimeters longer? Like I said, most things will stretch if you apply force. Not everything. Glass doesn't stretch very well.
Actually, they made bendy glass.
True, but regular window glass doesn't bend well. Trust me on that point. Really doesn't bend well. Metal bars bend or stretch a little bit. Rubber, some plastics, some metals bend quite well, like a spring is designed to bend. Yes?
I think I'll do, not to go too in depth, but like, you know how you superheat iron and stuff, and you can like reshape it all?
Well, what you're doing there is you're actually more turning it into a liquid.
Well, it's actually more like clay.
True, but it's technically not a solid because it will flow to take the shape of the container if you leave it long enough. So it's, well, it does depend. Well, getting off track. Yeah, freaking hot. Now, getting back to this, I need to know the force. Now, come here, boy. Come on. All right, be a poo head. And it's not turning it. All right, this way. All right, stay. Doing that again. All right. So since it's decided not to rotate, I'll just move it manually.
Yeah.
That created a lot of vertigo for whoever's watching that video. Whatever. Now, shh. Don't care. Don't have the authority to do it. F. What answer is it? What's my answer? How much force do I have to do to stretch this 2 millimeters? What's wrong with this angel? Louder? I do. I said I want to stretch the bar 2 millimeters longer. How do I do that? Grab and pull. How much do I have to pull? So Trixie, what's the matter with this question? Yes. What's wrong with 2 millimeters? It's supposed to be in meters, so that should be 0.002 meters. So how much force do I have to apply? No, milli is 1,000. So you divide by 1,000.
10 millimeters a centimeter?
Yes. So Ryan, how much is that?
He's playing.
Target number 1 with the Gatling gun. Okay, Kyle, if you want to play with the Gatling gun at the end of class? And then,
Can I see an answer?
yes.
Negative 3,000.
Yeah, 3,000 newtons of force.
She's right. Of course I'm right.
Now, okay. So, and Ryan, thank you for volunteering to help me with this one.
Yes.
Car shock absorber. Sorry, presses. So the car shock absorber compresses from 31 centimeters to 27 centimeters long when an 88 kilogram person gets in. Besides the fact you need new shocks, what's the spring constant K? Now, what have I given you? No, I've given you mass.
Mass.
And what do you need? Well, hang on. Let me rephrase that. The first thing I expect you to do is draw a picture. Now, before, actually no, that's upside down. Shock absorbers like this, and it's 31 centimeters. Then what happens? Mr. Sutton gets in the car, and the shock absorber is now what? 27 centimeters. Now, smile. Now, what's happened? Mr. Sutton's gotten in the car. Woohoo! Definitely need new shocks. And what has Mr. Sutton done to the shocks? He's compressed them by 4 centimeters. How did he compress them? Force of gravity. Yes. Force of gravity, which is mg. So what's the force we're applying on the spring? I don't know, but you guys can calculate it for me. Hurry up.
860.
That's 88 kilograms times 9.81 meters per second squared. So that's my force. What's the distance the springs have compressed? 0.004. 0.04 meters or 4 centimeters. Can you tell me K for these springs? Louder?
Yes.
Of course you can, because you've got it done, and you're sitting there waiting for these boys to get done, which is why I'm going to give you the Gatling gun soon. Yes. 4 centimeters. 4 centimeters times 1 meter. 100 centimeters. 0.04 meter. Okay, come on. What am I getting for K? F equals minus kx. How do I solve for K?
863 divided by 0.04
K equals minus F over X. 863 newtons divided by 0.04 meters is what?
Negative
21,575 newtons per meter. Seems reasonable. Stretch that thing a whole meter is a lot of force. So far, so good? All right. Last question for you before we go do the lab and play with the Gatling gun. I am going to talk about, there's potential energy here I want to talk about, but I want to do the lab first. So everybody sees that K is 21,000? All right, good. Now remember that number, because then Og, Mr. Sutton's little brother, pulls out the 295 kilogram engine block. Yeah, reaches down, grabs it, picks it up.
My dad knew some people that could do that.
My brother used to be able to do that. I don't know if he still can. That's 295 kilogram engine block. My question is, how high do the shocks lift? If you can get that right, I'll give you your lab and your homework. But you get, sorry? Same truck, same K. That's what I told. That's why I told you to write it down. Pulls out the 295 kilogram engine block. How high does the springs go? A lot. I don't. Well, he probably didn't take the head off or anything else, but yeah, just lift the whole thing out. Kind of scary. Yes. minutes, I'll show you his baby. Yes?
This probably isn't right. This isn't actually.
I have no idea. It should be. Actually, I should say that. I'm supposed to know this, and I'm supposed to remember this, but
Okay, so 2.
yes, minus kx. All right. So, plug the numbers in. Please show me, tell me. Then you get your homework in the lab. And if you're done early, we get to play with the Gatling gun. Yes? I don't know. Actually, I think you're right. Right.
What's your summing for x?
When you get to 13 centimeters.
How do you get that on the next question? Okay. So, people that answer, show me their work first, get the lab. People that don't show me their work, get the lab later, and you got to work on it the hard way. Now, it is 13 centimeters, but you got to prove it. All right. Now, thank you for being brave enough to admit that. Now, one formula. Force equals minus kx. The force you apply depends on the spring constant, how springy it is, and the distance you stretch it. You have a little brother or sister? Big sister. When you were small, did she ever pick you up? Okay. Imagine you grab a cat by the tail and start swinging in a circle. Now, I certainly hope the cat crawls up your arm and slashes your face for doing it, but just imagine it. So what's going to happen if you string it really fast, swing it really fast? No, you're going to stretch it. It won't be happy, and it really should get even with you later. As much as I joke about torturing cats, that's just wrong. So you can stretch most things. Like the tail of a cat, your arm bone will stretch a little bit. It's pretty brittle and it'll snap soon, but it does stretch a little bit. Rubber bands stretch a lot. So here we have our, hang on, if you've got the answer, come grab the homework. We've got our spring here, the shock absorber, which is basically a giant spring to keep your car from going go as you drive down the road. Now, there we have a 295 kilogram motor resting on top of it. Now, to be simple, yes, there are 4 shocks. I'm just drawing one because I'm lazy. Okay? Now, how much force is that 295 kilogram engine block putting on that? That's mass. Force of gravity is going to be pulling that down. Now, sorry, Kyle, you said something. It's 295 kilograms. Acceleration to gravity is 9.81, so that's a total of 2,700. I don't know. You have the calculator. You tell me.
Ooh,
2,893.9, 2894 newtons. Okay? Now, we take the engine block off. What happens? Well, we were compressing it by applying force. Why is that? You're supposed to be over here. Come on. Come up. This way. Screen. All right, try this. And now you won't turn, but I can hear the gears grind. There's logic and reasoning in this. All right. Now, guys, so I'm explaining this to Kyle because he needs a little extra practice. If you've got it, 13.4 centimeters, grab the homework, grab the lab, start reading the lab. I'll go over that in a couple minutes. Now, so say 2,894 newtons of force, so we know we're compressing this. Question is, how much are we compressing it? Well, the formula is right here. Force equals minus kx. Now, like every physics 20 formula I ever give you, I give you enough information, all the information except for one of the variables. And you got to figure out which one I'm asking you for. I'm giving you the force. Well, I've told you k, and I said orally, how much does it stretch? So, we're solving for x. Now, I'm hoping that you can rearrange the equation like that, because that I find conceptually easier. Now, I gave you the force, minus 2894 newtons. And we calculated K earlier. You should have wrote it down. 21,575. And you do Mr. Math. Actually, ask Mr. Calculator to figure it out for you. And you give me a number. A negative gives you a direction. Just don't worry about the negative for the moment. How much is this stretched? How much is this compressed?
0.1.
So if I take the engine block off, I'm taking that force off. It should stretch back 13.4 centimeters. All right? Grab the homework and give it a try. Now, there is a part 2 to this, potential energy. I'll do that later. And of course, I can't pause the video, so it'll be part 2. Have fun. The survivors after the Gatling gun will be back. Please, Lobos.